Dennis Jin, UR14CS319, and I'm here to explain the sixth experiment of compiler, which deals with single pass assembler for SIC. So we'll start out with what is an assembler. An assembler is basically it basically converts assembly language into object files. Object files contain a combination of machine language, machine instructions, data, and information needed to place instructions properly in the memory. assemblers are needed to assemblers are needed to translate assembly instructions and pseudocode instructions into machine language equivalents or machine instructions. So let's take a look at the code. Okay, first we have our header files here, followed by the main class. Inside the main class, we first input the files. We open and read the input file. We have a couple of input files here: assembler, optab, intermediate, symtab, likewise a symtab and output. So we read that into memory, into the input, and then the next step is to read through, analyze these input files, and to see if the opcode contains start, and if that is the case, yeah. So if the line contains start, we do the following: we find if there is an operand field after the start, and initialize the LC to the operand value. And so our code is while I is less than or equal to the length of the words. If we have an if loop inside the while, if the words equal to start, then we set n equal to I and increment the value of I afterwards. And if the length of the words is greater than n, then LC is equal to parse int words n plus 1 and system.out print the value of LC. If that's not the case, then we set LC equal to 0, and then we move on to the next line. We have a string opcode. While I is less than the length of the words, we have if optab contains words. We split it according to the space, and then we write the LC, the value of LC, which was in this case it will be while j is greater than the length of the op. It contains the array, and then the opcode will be set to the opcode value, the value of j plus I in the array op operand. And then we print the following: LC plus the space, the value of LC plus the value of opcode plus the words in the array. And yeah, so and then we have our next block here. If the word does contain if the opcode is word, then we are told to increment the LC by 3. If the opcode is byte, then we increment the value of LC by 1. If the opcode is RESW, then we increment LC by integer equivalent of the operand value of 3. Of the operand value. So yeah, so likewise the same is done here. And lastly, if the opcode is RESP, 0 byte, then the increment LC, or then increment the LC by the integer equivalent of the operand value. Yeah, so that's that. And then if there is no symbol or label in the operand field, then the operand address is assigned as 0, and it is assembled with the object code of the instruction. So that's that. And oh yeah, we also write the process lines in the intermediate file along with their along the location counters. And then after that, we find the the next step would be to find the length of the program. As we subtract the starting address from the program of the LC. So length is equal to LC minus the start. BW.flush, we call the function b2.flush. Then we have so then we have this statement here: while y is equal to br4 dot readline is not equal to null. We check if the send table is equal to null. If yes, then syntab is equal to y. Else syntab is equal to syntab plus concatenate the value plus y, space plus load the y. The same goes for this one. If length is equal to br dot readline is equal to null, then we have three variables I, j, and f. We split it according to space, and then if if I is less than the length of the words, then the following gets executed, and you replace all the words with the line. You split the words according to the space. If line contains start, then we do the following: bw.write, where we have h plus the words plus the division, which in this case is about, followed by the words and then length. The same goes for the text portion of our object code. We use T to represent this area, the text portion, and E to represent the end of the code. So we have that, and then the value of the starting address, which is always given at the end of the object code. So let's take a look at our resultant program. So we have this 1000, alpha and beta from the following, from the input that we have given. That's our output there, and that concludes our experiment.